Okay, so good morning, everyone, or good afternoon, or good evening. I don't know where you are on the planet. So I'm going to be speaking about the pizza theorem. Hopefully I'm loud enough. I have no idea. And I'm actually standing because I'm used to talking and standing. So this is joint work with Richard Ehrenborg and Sophie Morel. And here's a list of places that have funded us in order so that we can work together. I mean, this is actually coming out of a series of papers, though I'm focusing on one in particular. All right, so pizza. What is a pizza? So a pizza you should think of as a disk in two-dimensional space. And what do you do with a pizza? We share a pizza, of course. Okay, so I'm going to pick a point. So what do we usually do when you have pizza? You pick the center, you cut it with, 4 big cuts, you have 8 slices, and you share it with your friend. So we're going to be a little bit more creative, which is we're going to pick a point, not necessarily the center. In fact, we're not picking the center. And we're going to cut with these 4 cuts. So these 4 slices are equally spaced lines through the point A. So these are equal angles. And of course, we want to share. Share with a friend. So you have your 2 friends, plus and minus. And the result is that if you look at these 2 friends, they have the same amount of pizza. So this is due to Goldberg in 1968. So let's say some history about this. Oh, I don't know why this equally came up funny. All right, so the original pizza problem was stated by Upton in 1967 in Math Magazine. And Goldberg, not only did he prove this for an even number of lines, so not only for 4 lines, but in general, even number of equally spaced lines. In the case when k is equal to 2, so we have 4 lines, Carter and Wagon gave a dissection proof. When you have these cuts and you rearrange your 2 volumes, two areas and get the same, move one area to the other. Then there's Hirshhorn, and Hirshhorn considered the case of P people sharing pizza and showed you could do this. So, and Maubrey and Dyerman showed that in the case of an odd number of equally spaced lines, the pizza theorem doesn't hold. So for example, you can't just have 3 big slashes and sharing 6 pieces with a friend. It doesn't work. And Fredrickson extended Carter and Wagon's result dissection proof in the case of k is equal to 2 to even number of slices. All right, so the classical proof of the pizza theorem is that you have this picture and you have your lines and you rotate it slightly. And you can, for example, pass to polar coordinates and look at this. So this is it's using analysis or calculus. But you should look at these lines and say to yourself, well, this reminds me of something because we are combinatorialists. And the way you should think about this is let's label these cuts. So we have the line y equals 0, the x-axis, x equals 0, also the y-axis, the line y equals x, the line y is equal to negative x. So this is very indicative of the type B2 hyperplane arrangement. So what we want to do is actually go much more generally, and we want to think about the pizza theorem in higher dimensions. And so let's start filling this up. So let's assume we have a real vector space V that's dimension n, and it has an inner product. And then we're going to let E be a finite set of unit length vectors. And for given one of these unit length vectors, the hyperplane H sub E just consists of all vectors that are perpendicular to this given vector. And then we have this collection of hyperplanes forms our hyperplane arrangement, where our index set is E, capital E. We should also recall what a chamber is. So you have your arrangement, and you're going to look at the complement of the arrangement, and all a chamber is a connected component of the complement. So we're going to let script T denote the set of chambers, and we're going to select a base chamber. So here I have T sub 0 indicating that. And associated with each chamber is going to be a sign. It's -1 to the separation set. So if you're standing in a chamber, it's how many hyperplanes do you have to pass through in order to go from your current chamber to the base chamber. So, the base chamber here has, sign +1, and depending upon how many you pass through determines your sign. All right, so the next thing I want to define is the pizza quantity. So, okay, so we were working with a pizza, but again, we're going to be bumping this up more generally. So let's let K be a Lebesgue measurable set that has finite volume. And the pizza quantity is that we're going to take your set K, we're going to intersect it with a chamber and look at the volume of that, and it's going to have a sign associated with it. And then we're going to sum up over all possible signed volumes that we have here. So again, you can see this picture. All right, the other thing is, because I mentioned type B2 arrangement, we have to start talking about Coxeter arrangements and Coxeter groups. So I'm going to have script HW is a Coxeter arrangement. So you have in the background this group that's generated by orthogonal reflections in the hyperplanes of script H that has to be finite, and the arrangement is closed under all such reflections. So if you fix a hyperplane and you start reflecting the other hyperplanes over that, everything is fixed. So it's nice, it's closed rather. So as an example would be the dihedral arrangement I2 of M. So it consists of M lines. Something else that we're going to need is the notion of the product arrangement. So if HI is an arrangement in your space VI, we have a notion of a product of two arrangements. And the thing that's going to be important for us is that if you have two Coxeter arrangements, their product is also going to be a Coxeter arrangement. So now we should actually say something about Coxeter arrangements, all the different flavors there are. So type AN, so a nice way to look at this is that declare your vector space to be the set of all vectors where the sum of the coordinates is 0. So we're looking at a subspace of this just to have it a little bit easier to define. And all those hyperplanes are going to be of the form xi is equal to xj. And the thing that's going to be very important for us is actually the case when n is equal to 1. So a sub 1. So that just consists of this one-dimensional line, and the hyperplane is the origin. So just this one point. The other arrangement, this product arrangement that again is going to be a very important special case, is A1 to the n. And this is a product of A1 with itself n times. And the way you can think about this, it's all the hyperplanes defined by xi is equal to 0. I goes from 1 through n. So in other words, the coordinate hyperplanes. All right, then we have type B and C. So here we have the coordinate hyperplanes, and then we throw in these additional hyperplanes. Xi is equal to plus or minus xj. So geometrically, this corresponds to symmetries of the n-dimensional cube and the n-dimensional cross polytope. I guess I didn't mention in type A, that this corresponds, AN corresponds to symmetries of the n-dimensional simplex. So these are very geometric. And then we have type DN, where we drop the coordinate hyperplanes. Okay, E6, E7, E8. I'm not going to say much about them other than there's a lot of elements. Type F4, this is a very nice Coxeter arrangement corresponding to symmetries of the 24 cell. And we have type G2, type H3 and H4. So again, H3 symmetries of the dodecahedron and icosahedron, H4 symmetries of the 120 cell and the 600 cell. And then again, going back to I2K, symmetries of the K-gon. So here I have pictured symmetries of the 6-gon, consisting of 6 lines. All right, so given this language, we can restate Goldberg's result. So that corresponds to the hyperplane arrangement is the dihedral arrangement, I2 of 2K, where K is at least 2. We have at least 4 cuts, 4 lines. And for every point, so now we want to figure out, where are we going to be making the cuts at the point A? So the thing that we require is that if you have a bowl centered at A of radius R, the origin has to be in that bowl. And then in this case, then what happens is that the pizza quantity is 0. In other words, you can share this pizza with a friend. We also want to look at more general regions. So let's describe what it means for a set to be stable. So what that means is that if you have the set and you take an element from the Coxeter group and you apply it, you still have the set. And that holds for all elements in your group. So here's an example of a set. I was trying to draw a 4-leaf clover kind of thing. All right, so now let's actually look at this more general pizza theorem. So let's suppose we have a Coxeter arrangement and the negative of the identity is in this underlying group. So I'm going to say more about that very shortly. And we're going to assume we're not of type A1 to the n. So we're not in this case with coordinate hyperplanes. And we also have to assume that our set K is stable by the Coxeter group. And now we're going to pick this point where we're going to be slicing through. So the requirement is that when you pick this point A and you apply all elements of the Coxeter group and you look at their images, you take the convex hull, that set has to be contained in this stable set K. So those are the conditions. Then in that case, the pizza quantity is 0. In other words, you can share this pizza with your friend. So to say something about special cases of this, so Fredrickson in 2012 proved that in type A1 cross A2 of 2K, that this holds for balls where we have at least K to be 2. And then recently, Brailoff proved that in the case of BN, of the Coxeter group, type BN also holds for balls. So again, going back to this theorem that I stated, this is for much more general sets and many, many Coxeter arrangements, not just BN. All right, so let's actually say something about this condition, the negative of the identities in the group. So it turns out that this is equivalent to the fact that H is a product of arrangements of the following types. So A1, Bn, when n is at least 2, D of 2m, so D of even number, E7, E8, F4, H3, H4, and then the symmetries of the 2K gon. So the things that are missing are AN, D2M plus 1, E6, and I2 of an odd number of lines. So let's actually say something about this case, A1 to the n. So, because this is a special case. And again, remember in the theorem, we threw this one out. This said no type A1 to the n. So let's actually look at this. So here's an example. So I have my arrangement, and here we are. And what's happening is, here I have my signed pieces. So to figure out what's going on, I'm going to add some helper lines. So I'm going to add the line x is equal to 2a1 and y is equal to 2a2. And, same signing in all the regions. And if you look, there's a lot of cancellation that goes on. I mean, you can see these regions over here on the left. I hope you can see my pointer. Cancel with these regions over here on the right. This top middle region cancels with the bottom. And all we actually have something left. We have a rectangular region here. So you can see that. So, and the area of that region is 2a1 times 2a2. And the general result is, in this case, that the pizza quantity is actually 2 to the n times the product of the coordinates of the point A. So again, it's non-zero. All right, so how do you prove these kind of things? So what happens is that it is analytic. You have to study the derivative of the pizza quantity and how it changes when we shift the picture a little bit in the direction V. And the thing is, we would like to avoid this kind of a proof. So what we really would like to do is give a dissection proof. All right, so what are we trying to do? We're trying to show that these signed volumes, the union of them is equal to 0. So the whole point for a dissection proof is we want to show the volume of the pieces that have sign +1 is equal to the volume of the sign of the pieces that have sign -1. So here's the more general setting we're going to be sitting in. So this is a little bit of a setup. So let's let script C of V is going to be a family of subsets of V. It's going to be non-empty, and it's going to satisfy the following conditions. So it's closed under finite intersections, closed under affine isometries. So if you have such a set and move it around, it's still in the set. And if you have an element in the set script C of V, and if you have a closed affine half space and you intersect it with your set, we want that intersection to still be in this family. And also, we want it to behave nicely under products. The product of two such subsets is, again, going to be in this family on the product of the underlying spaces. So there's many examples of these. I just listed 2. So for example, convex subsets of a vector space satisfies this. Convex polyhedra satisfy this. So it's a very natural condition to have. All right, so now we're going to continue to bump things up. We want to consider the free abelian group generated by this elements in this script C of V. And what we're going to do is use K of V is going to denote the following quotient. So we're taking this free abelian group generated by all the elements of script C of V, and we're going to mod out by the following relations. So the first relation is that this bracket of the empty set is 0. And then it satisfies, these classes satisfy this nice inclusion-exclusion formula. So we're modding out by that. And also, if you apply an affine isometry to an element in script C of V and look at its class, it doesn't change the class. And in general, if you're just given such a subset from script C of V, we're going to put brackets around C to denote its image. All right, so what does it mean for 2 elements to be in the same class? So in this setting, because we've modded out by all of these things, it means that if two such elements are in the class, that there is a dissection proof going from one element in a fixed class to another. So now, given this more abstract setting, let's define the abstract pizza quantity. So H is a hyperplane arrangement. I haven't said anything about Coxeter at the point. K is a pizza. So I'm using this very loosely now because I don't want to have to say all these qualifications. But okay, so what do? So again, we have our chambers in our hyperplane arrangement. We're going to intersect it with our pizza. And now we're going to be looking at these classes in this abstract setting. And we're going to assign them a sign in the usual way. And that's going to be our abstract pizza quantity. We're working in this, this abstract free abelian group. All right, so now let's state the abstract pizza theorem. So again, now we're in a Coxeter arrangement in an n-dimensional space. The negative of the identity is in the group. Again, we're assuming it's not type A1 to the n. We have a subset in script C of V and a point in the vector space V. As usual, we assume the set K is stable by the group and contains the convex hull of all these images of the point A. And the result is that the abstract pizza quantity vanishes. So again, what this means is that this identity holds in K of V, that there is a dissection proof. All right, so to say something more about what goes on with the ideas of how this works, so we have to recall pseudo-root systems. So we're using this language because, we say root systems in combinatorics when really the rest of the planet says pseudo-root systems. I mean, people who are in representation theory do that. So, this was a big discussion we had with Sophie. So phi in the vector space V is a pseudo-root system. So we have a finite set of unit vectors, and that if you apply an orthogonal reflection in the hyperplane H sub B to the vector A, it's still in the set. So it's nice and fixed. And in fact, this condition B, if you look at the case when alpha is equal to B, if alpha is in your pseudo-root system, then the negative of alpha is in there. So once you declare your vector, whether you're going to have it positive or negative, then let's say if you say it's positive, then the negative of it is in there. So it makes sense to talk about the positive and negative pseudo-roots. All right, the next thing we have to talk about is two structures due to Herb. Okay, so we're in the pseudo-root system. Situation phi with your Coxeter group W. And a two structure is going to be a certain subset of your pseudo-root system. So the first thing it has to satisfy is that it is a disjoint union of pairwise orthogonal subsets of little phi. And each is of the following type. So there's three different types you can be for two structures. You're either type A1, type B2, or I2 of 2 to the K. So symmetries of a 2 to the K gone here. And here K has to be at least 3. And the second condition on a two structure is that you can intersect small phi with the positive roots of your pseudo-root system. And if you have an element in your Coxeter group and it sends phi plus to itself, so here's little phi in your two structure, then the sign of W is positive. So, okay, so where's this two structures coming from? So I'm just going to say something very briefly now, and I'll say more at the end. So this comes from Herb was studying characters, was studying discrete series characters of representations. So again, I'll say more about this later. All right, so let's let capital T of phi denote the set of two structures of your pseudo-root system. And there's some very nice properties that two structures of a root system satisfies. The first is that the group acts transitively on them. And because of this, that all two structures of a given pseudo-root system have the same type. So let's actually just record the root systems, look at their type, and also the type of the two structures. So here we have this big table. And if you look at this closely at the rank of a root system versus the two structure, some of these are the same. For example, if you look at D of 2M is the pseudo-root system, and then the two structure is A1 to the 2M. So that has the same rank. And in fact, that if phi is your pseudo-root system and you have its associated two structure, when the two ranks are the same, that's equivalent to the negative of the identity is in your Coxeter group. Also, we have a very natural way. Each two structure has a sign. And there's some very nice properties. So for example, if you look at all the two structures in your set, T of phi, and you add up the signs, you get 1. And then also, if you're in the case when you have W sends phi intersect the positive roots is contained in phi plus, then the sign is well behaved. Okay, so here's the theorem. This is one of the theorems. So let's suppose we have a pseudo-root system where all the vectors are normalized. So they're unit vectors. And we're going to let's choose a positive system. And we have the associated hyperplane arrangement corresponding to the positive pseudo-roots. And you have a base chamber corresponding to everything pointing in the positive direction. And then given a two structure, phi of the pseudo-root system, we're going to let H phi be all the hyperplanes corresponding to the positive two structures. And of course, it's based, so this is a subset of this bigger set phi at the beginning, the normalized pseudo-root system. So because of that, its base chamber that's positively signed, all positive signs, contains the base chamber of your original arrangement. Then what happens is that when we're computing the pizza quantity of the arrangement H of K, that we can actually reduce this to a sign of abstract pizza quantities of these two structures. So this is a way to have something that's, complicated, and we have these smaller structures. And remember, there's only 3 possible types you can have for these two structures. So this is really going to give us a way to get a handle on this. So the abstract piece theorem says the following. So again, we're in this Coxeter arrangement setting. The negative of the identity is in your Coxeter group. Again, the set K is in script C of V, stable by the Coxeter group. And this point is chosen so that if you look at all the images with respect to the Coxeter group, it's in the set K. So if we're in the situation where we're not type A1 to the N, then the abstract pizza quantity is going to be 0. And again, viewing it in this abstract setting. And if you are type A1 through the N, and phi is the normalized pseudo-root system, and again, we have phi plus, the positive system, corresponding to the base chamber of your original H, then the pizza quantity, the abstract pizza quantity in this setting are these classes. Now, I guess I have a typo here. Let's see that on the right-hand side, that open bracket should be a closed bracket. So that's my mistake because I wanted to have the classes here. Okay, so let me say something about the proof, just to give you, this is very, very brief sketch. I mean, there's a lot that's going on here. So the first case would be the 2 structure contains a factor of B2 or I2 of 2 to the K. So in that case, what happens is that we prove the abstract pizza quantity is 0 by, remember, we're dealing with these product arrangements. So, and we can reduce it to the 2-dimensional case here, and we have to move pieces around. So you see pictures like this in our paper. So this is sort of the pain, because remember, we're doing these dissection proofs. So let's recall the Wallace-Bolyai-Gurwine theorem with scissor congruence. So if you have 2 polygons, it turns out that, so this is living in 2 dimensions, they are scissor congruent if and only if they have the same area. So, again, you have 2 polygons, you want to be able to cut one up with scissors, finite number of pieces, rearrange it to the other one, and you can do that if and only if they have the same area. Hilbert's third problem asks, can this happen in general? And the answer is that no, for dimensions 3 and above, this is false. But actually, this is true in the case of parallelotopes. This has been shown. So that's actually a case where Hilbert's theorem does work. So now let's go back to this second case in the abstract pizza theorem when your 2 structure has type A1 to the n. So here, the abstract pizza quantity looks like this. And let's see. And then what happens is that so here the abstract pizza quantity looks like this. And this is for the 2 structures. And what happens then is that when you look at the abstract pizza quantity of the original arrangement, it's going to be a sine sum of these parallelotopes. And the fact that by using this extension of Wallace-Bolyai-Gurwine, in the case of parallelotopes, all these sine sums, they cancel and you actually get 0. So, the pizza theorem, all these pizza theorems, abstract pizza theorem, it's not, you can actually extend this to not just volume, but the intrinsic volume. So let's just recall these. My phone is ringing. Let me hang it up. Okay, I took it off the hook. So today's the first day of classes. I didn't dare go on campus because there would be no internet, actually. So that's why I'm at home. So, all right, intrinsic volume. So Vn is usual n-dimensional volume, but we have other things. So Vn minus 1 up to a constant is surface area. Going all the way down to V0 is the usual Euler-Poincare characteristic with compact support. And it's a theorem of Hadwiger that says, suppose you have a valuation that is invariant under rigid motions, and it's continuous on compact convex sets, then you can actually write it as a linear combination of these intrinsic volumes. So these kind of movements, they're encoded well. So it turns out that if we're back in the case of abstract pizza theorem, same assumptions. So we have 2 cases. So the first is that if our Coxer arrangement is not type A1 to the n, then the identity, this alternating sum of these intrinsic volumes is equal to 0. So like if you fix the ith intrinsic volume, and so, for example, if you look at the case like n minus 1 is surface area, this says if you have your friend and you want to share your pizza, or your abstract pizza, that you have, for example, the same amount of crust in 2 dimensions. And if you are of type A1 to the n, and we have to actually further assume that our set K is convex, then again, you have sharing holds for all intrinsic volumes from V0 up to Vn minus 1. So remember, Vn is the case when it's non-zero. So that's why we have that condition. Okay, other results. So let's go way, way, way back at the beginning, classical pizza quantity, volume, and let's look at the case of balls. That's going to be our set K. And if we have a Coxeter arrangement in n-dimensional space, let's assume, excuse me. I took the phone off the hook and then it's making noise. Okay, so let's assume the number of hyperplanes has the same parity as your space. And let's also assume the number of hyperplanes is strictly greater than the dimension of your space. And as usual, we assume the origin is in the ball centered at A of radius R. Then we can conclude the pizza quantity is zero here. The volume is zero. We share. Now, the problem here is this result uses calculus. The thing we should point out, this condition that we've always had, this negative of the identity in the Coxeter group, that actually implies that the number of hyperplanes in the arrangement and the dimension of the space have the same parity. So this theorem also holds in other types, AN, equivalent to congruent to 0 and 1 mod 4 and E6. The question is find a dissection proof, because again, the problem is this uses calculus or analysis. More open questions, understand type AN when n is congruent to 2 or 3 mod 4, and type DN in certain cases. So Marbury and Dyerman showed, again, that you don't have this pizza sharing theorem. And so they actually showed this result. So let me say something. What does this mean? So this is the case when I2 of M when M is odd. So we have two cases. M is equivalent when we have our number of lines is equivalent to 3 mod 4 versus 1 mod 4. And it says the following. So in the case when M is equivalent to 3 mod 4, you should, if you are a greedy friend, I mean, I don't know if you can be called a friend anymore, you should take the piece of the pizza. The first piece you should take is the one where the origin is sitting in it. You will actually end up with more pizza. You'll have a positive amount, once you look at the signed areas, versus if M is equivalent to 1 mod 4, you're not a very nice friend. You give your friend, say, oh, take this piece here first that has the origin in it, and they're going to end up with less pizza. Okay, going back to the Hirshhorn family, you probably guessed these people are related. They definitely are. So they were looking at the case of P people sharing a pizza, which is the dihedral arrangement of type I2 of 2p. So we have 2p lines, 4p slices. So each person takes the pth slice and you actually get fair distribution. So here you're seeing each person's getting p slices and it's very happy family. So it's open about when you have at least 3 people and at least 3 dimensions, which arrangements are going to actually give us a fair division of the bowl. We have really no idea. There is one solution, and I guess I'll quickly say something about it. So this is the case when P and the dimension is 4. And so we have 2 hyperplane arrangements here, H1 and H2. You can check that each has type D4. Their union is type F4. And so now we're in this union H, script H, and if we look at a chamber of H, and we let Ti be the unique chamber in H sub I that contains T. And if we do this, if you look at the sign of T, it's actually, you can split it up in as a product of these chambers in these other sub-arrangements, or these other, I should say other arrangements, sub-arrangements. And then we're going to have 4 people, and they're going to be encoded by these signs, so in your chamber. So we have the person plus, 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 minus, minus, plus, and minus, minus. So what happens is that because this arrangement H1 satisfies the pizza theorem, you can show that the amount of pizza that person plus plus gets versus plus minus gets, those 2 volumes add up to half a pizza. And same thing with H2, you get a relation with 2 of the people, and the arrangement H, you get a relation there. And when you solve this very easy system, you find out that each person gets a quarter of the pizza. So it is a fair, you're sharing fairly. What to do in general. The last question I wanted to say was to say something about these 2 structures. So this was just so amazing when we found out about 2 structures and, learning about this work of Herb. So where was this coming from? So Harish Chandra in 1965, he gave a character formula for stable discrete series constants of a real reductive group. This involves, there's all kinds of work he was doing, but finding this character formula, this was a central step in Langland's classification of all representations of the real reductive group. And Herb actually found a direct formula for this via 2 structures. So she was the one that had this insight that somehow you had to look at the sort of these easier cases. Another formula for the Harish Chandra character formula was given by Goreski, Kotwitz, and McPherson. And so in other work with Richard Ehrenborg and Sophie Morel, we actually generalized the Harish Chandra character formula to arbitrary Coxeter groups. And this language that I used for Herb's 2 structures, this was actually something that we did. We actually had to recast this. And what does this mean for finite Coxeter groups? But again, this whole idea that, where else can you use this idea? The fact that there are, things are well behaved, the signs are well behaved in these cases, when you look at the 2 structures. So that's where I really want to leave you with, because this is really connecting combinatorics with algebraic geometry, number theory, representation theory. So that's all I have to say for today. Thank you very much.
Margaret, thank you very much for a very interesting talk.
You're welcome.
And now, could you please stop sharing?
Okay, stop the share.
Okay, great. Any questions, please?